Component 2. Hello, National Program 211 Review Panel members. I am Ray Bryant, coming to you from the pond in my backyard, where I am adhering to stay-at-home guidelines here in central Pennsylvania. I am the lead scientist for the Water Quality Project at the ARS Research Unit located at University Park, Pennsylvania. We are located on the Penn State main campus, centrally located in the Chesapeake Bay watershed. We also have a branch location at the University of Massachusetts Cranberry Research Station near East Wareham, south of Boston. You heard about one of those accomplishments from our location in Component 1 presentation. Component 2 is about erosion, sedimentation, and water quality protection. Component 2 has 5 problem statements, and we will be reviewing accomplishments in each of these problem areas. The first problem area looks at field-scale processes controlling soil erosion and the transport and fate of sediment and contaminants. The first accomplishment is the development of a new method for sediment source fingerprinting. In order to study and understand field-scale processes that control soil erosion and the fate and transport of sediment, we need methods for estimating sediment source contributions within watersheds. When we observe and sample sediment accumulations, we want to know where in the landscape did that sediment come from. Previous studies relied on a single optimum composite fingerprint with a minimal number of tracers. ARS researchers in El Reno, Oklahoma, developed a new multiple composite fingerprints method for estimating sediment source contributions in watersheds. Cesium-137 is commonly used as an optimum fingerprint. In this study, ARS scientists compared results using Cesium-137, the traditional approach, to results obtained by analytically solving a 3-end member mixing model using a multiple composite fingerprint approach. In this case, samples from surface soils, gully banks, and sediment deposits were digested in acid, and a group of 27 elements were measured by ICP mass spectroscopy. First, tracers, the individual elements, were screened to identify the best elements for use as a tracer. The remaining elements were paired to form a group of 40 two-tracer combinations, i.e. a fingerprint, and they were evaluated. These 40 pairs make up the multiple composite fingerprint. There is a wide range among these 40 individual fingerprints. In the chart, you can see that 4 fingerprints estimated rangeland contribution, shown in green, to be 0.1 or 10%. 1 fingerprint estimated the rangeland contribution to be 0.9, and 15 fingerprints estimated the rangeland contribution to be 0.5. However, the mean across all 40 fingerprints is 35%, plus or minus 3% standard error. The new multiple composite fingerprints approach provides more accurate sediment source estimation, and this is vital for soil conservation planning and for validating and improving spatially distributed erosion models. The second accomplishment in this problem area introduces the use of geophysical methods to evaluate earthen dams. There are over 11,000 flood-retarding dams in the U.S. that were constructed by USDA Soil Conservation Service, now Natural Resources Conservation Service, beginning in 1944. These earthen dams have a design lifespan of 50 years and need to be evaluated for integrity. Only non-intrusive methods can be used for fear of otherwise weakening the dam. The University of Mississippi, in collaboration with ARS researchers in Oxford, Mississippi, the Natural Resources Conservation Service, and Mississippi's Department of Environmental Quality, have been studying the added value of incorporating geophysical information into visual assessments of dams and levees. This is an aerial picture of Carroll County Dam, a high-hazard dam located in northwest Mississippi. A seepage study determined that the dam was affected by moderate seepage and sand boil formations. The purple dots in the upper left plot are anomalies detected by seismic refraction, and the light blue dots in the lower left plot are anomalies detected by electrical resistivity. These anomalies line up well with known locations of old channels shown in the marked up photo on the right. Results indicate that seepage was most likely taking place through a small lens of silty sand embedded within a clay layer below the dam that was not properly sealed during construction. This accomplishment shows the potential for finding faults and preferential flow zones in earthen dams and zones that should be investigated further. The second problem area under Component 2 deals with in-stream physical and biological processes controlling contaminant fate, transport, and effects. The first accomplishment is the development of a means of measuring gravel transport using impact plates. Gravel, which had been stored in a reservoir, began moving downstream following the removal of two dams on the Elwha River in 2012 and 2014. The entrained gravel could potentially cause channel instability and capacity issues downstream, so the gravel needed to be measured for both engineering and ecological reasons. The U.S. Bureau of Reclamation installed steel plates with accelerometers in the bottom of the channel downstream of the dam. The accelerators detect both amplitude and frequency of sounds made by gravel striking the plates. The signals were recorded, but they did not have the calibration needed to convert the data and find out how much gravel was moving downstream. ARS researchers at the National Sedimentation Laboratory in Oxford, Mississippi, constructed a laboratory flume equipped with exact replicas of the impact plates installed in the Elwha River. The photos show the plate system in the Elwha and the plates in the flume at the National Sedimentation Laboratory. Just behind the plates, you can see the entrance to the independent measurement system that was used to obtain sediment load data. The gravel dropped into the trap and was weighed before being recirculated automatically to the upstream end of the flume. Using this flume, they conducted experiments to collect amplitude and frequency data paired with known gravel size and amounts, and successfully calibrated to allow measurement of the number and mass of gravel particles moving in the Elwha River. Knowledge of gravel movement in the Elwha will allow river managers to adaptively manage the removal of the impounded sediment in a more informed and environmentally sensitive manner. This accomplishment measured reservoir sedimentation rates. Those 11,000 flood-retarding earthen dams that were mentioned earlier are losing capacity due to sedimentation. Sedimentation rates depend on variations in topography, soils, land use, and climate, the drivers of soil erosion. A team of ARS scientists in El Reno, Oklahoma, used bathymetric survey equipment to determine the current amount of sediment in the reservoir, the floodwater storage capacity, reservoir sedimentation rate, projected lifespan of the reservoir, and possible factors affecting observed sedimentation rates. They did this for 12 reservoirs in the Little Washita watershed in Oklahoma and found projected lifespans ranging from 45 to 118 years. Sedimentation of a reservoir serves as an integrator of erosion processes across the watershed and can be used to quantify the effects of multiple conservation practices that have been implemented through the years by Natural Resources Conservation Service. Quantifying the effects of conservation programs is the primary objective of the joint ARS-NRCS Conservation Effects Assessment Program that we refer to as SEEP. The third problem area in Component 2 addresses processes influencing the relationships between contaminants and aquatic ecosystems. This accomplishment evaluated stream impacts due to outdoor education class activities. Stream classes are popular, and many educational centers and similar organizations now serve thousands of students per year, which results in a high volume of traffic in the streams where their classes are held. No previous studies have evaluated the impact of these classes on macroinvertebrates. an ARS scientist in Columbus, Ohio, and a scientist from Mount Vernon Nazarene University sampled macroinvertebrates monthly for 1 year in riffles, runs, and pools in an agricultural stream site used for education purposes and a similar site unused by the education classes. When stream classes were in session, they found reductions in macroinvertebrate abundance in the top half of the bar chart and taxa richness, as shown in the bottom half of the bar chart, in riffles, but they did not observe differences when stream classes were not being conducted. Additionally, reductions in macroinvertebrate abundance and taxa richness did not occur in pools or runs, only in riffles. To avoid negative impacts on macroinvertebrates, educators should rotate activities among several sites and avoid repeatedly using the same stream site for their educational outreach efforts. Moving on to the fourth problem area, we look at the development and testing of cost-effective measures to control the transport and fate of contaminants in agriculture, urban, and turf systems. Dairy is an important industry in the Northeast. Most dairies are small, less than 100 cows, and they use a liquid manure system with lagoons, as pictured here. Liquid manure is too bulky to transport very far from the barn, so phosphorus gets over-applied to soils near the dairy barn. ARS and Penn State scientists at University Park, Pennsylvania, set out to develop a mobile liquid manure phosphorus extraction system that we call MAFEX, capable of treating dairy manure on 10 100-cow dairies or one 1,000-cow dairy. Most of the phosphorus in manure is in the organic particulate fraction. We designed a system that uses a screw press, centrifuge, and diatomaceous earth filter to remove consecutively smaller phosphorus-rich organic particles, and it fits on 2 tractor-trailer truck beds. You're probably familiar with a screw press and a centrifuge, but a diatomaceous earth filter uses vacuum to build a cake of diatomaceous earth on a rotating drum, and then liquid is sucked through the cake, trapping the finest particles. A blade scrapes the outer surface of the diatomaceous earth cake to clean it as it rotates. By adding ferrous sulfate to the liquid prior to passing it through the diatomaceous earth filter, we can remove 96 to 99% of the total phosphorus. All phosphorus-containing liquids are stackable and easily transported. Nitrogen is still present in the liquid and can be used on the farm. On liquid swine manure, the system works faster and with similar removal efficiencies. This accomplishment from the Eastern Corn Belt provides a broad look at nutrient balances, production and conservation practices, and their impacts on water quality. Nutrient loss, particularly phosphorus, from crop production agriculture has been linked to harmful and nuisance algal blooms in Lake Erie and other freshwater systems in Ohio. I'm sure that you remember the Toledo water supply system being shut down a few years ago due to toxic algal bloom. Using a paired edge-of-field approach, ARS researchers in Columbus, Ohio, in collaboration with Lake Erie stakeholders and partners, quantified the surface and subsurface water quality benefits of various crop production and conservation management practices. Edge-of-field drainage measurement is depicted in the bottom center picture. The upper left figure summarizes research that shows that nutrient budgets on farms in Ohio are near neutral, outputs approximately equal to inputs. However, the combination of discharge, the drainage leaving the field, and legacy phosphorus, that phosphorus that accumulated in soils due to previous over-application, significantly contribute to agricultural non-point source nutrient losses and highlight the need for regionally based conservation management. On the right side, promotion and adoption of 4R practices and, lower left, drainage water management using water control structures could potentially reduce agriculture's environmental footprint. In the top center, cover crops have a significant impact on nitrogen losses but not so much for phosphorus. These findings have been shared and delivered to Lake Erie stakeholders and partners such as Natural Resource Conservation Service, the Nature Conservancy, Lake Erie Foundation, and are being promoted to producers to help address eutrophication of Lake Erie. The last problem area in Component 2 encompasses development of new and innovative modeling and assessment tools to quantify sediment and contaminant transport in the landscape. The first accomplishment is development and adoption of design criteria for step spillways. Again, this accomplishment relates to the 11,000 earthen flood control dams that were constructed by SCS and NRCS since 1944. More than half the dams in this program have reached the end of their planned service life, yet they provide annual benefits of nearly $2.5 billion by providing flood control, rural and municipal water, irrigation water for crop production, wildlife habitat, and recreation. ARS scientists at Stillwater, Oklahoma, developed a systematic step-by-step design criteria for the construction of roller compacted concrete stepped spillways for application on earthen dams. The steps create significant energy dissipation compared to a smooth chute. Thus, you can have a smaller stilling basing footprint for step chutes than for smooth concrete chutes. The smooth chute requires reinforced concrete, which is more expensive than roller compacted concrete, and smooth chutes typically require a drainage system be installed underneath the concrete slab at additional cost. The USDA NRCS is adapting this criteria into their National Engineering Handbook. The U.S. Army Corps of Engineers are integrating the design criteria into their spillway design manual, and Federal Emergency Management Agency is talking about developing a design manual that adopts this design criteria as well. The graphic in the lower right outlines the step-by-step process for designing the minimum required training wall height for containing flow within the step spillway by taking into account the impact of the slope and step height. It is estimated that nearly 10% of the more than 11,000 dams will have roller compacted concrete step spillways incorporated into their dam rehabilitation design, resulting in an estimated construction cost savings of $600 million to $1.2 billion. The last accomplishment in this presentation of Component 2 reports development of acoustic methods for measuring sediment transport. Sediment transport is difficult to measure in streams because physically sampling the water sediment mixture typically requires personnel on site during runoff events. Researchers at the National Center for Physical Acoustics at the University of Mississippi and ARS scientists in Oxford, Mississippi, have developed, tested, and deployed numerous acoustic systems to monitor sediment transport throughout the watershed. Concentrations of suspended silts can be monitored and quantified using acoustic attenuation at 20 megahertz, and a coarse gravel transport can be detected by recording the sound generated by particles impacting each other during transport. The acoustic device developed at Oxford is often called the telephone because it resembles a large, white, old-style telephone. The telephone can measure silt and clay concentrations acoustically, which avoids fouling problems with optical instruments that are also used to measure sediments and extends the concentration range beyond optical instrument ranges. The figure shows example data from Rio Grande River near Santa Acacia, New Mexico. Note that measurements from the telephone, the red or orangish dots that overlap to form a line, compare well with the physical samples. Physical samples are the three blue dots with error bars that are partially obscured by other data. But you can see pick out the three error bars, and those dots do fall very close to the orange line. The green dots are data from other acoustic instruments deployed at the site by USGS or other agencies. These data also show good agreement with the telephone data. That concludes the presentation of Component 2 of the National Program 211 Retrospective Report. In closing, I would like to remind panel members that the complete description of accomplishments realized during this 5-year period includes the additional accomplishments found in the appendix. At this time, we can open it up for questions and discussion. There are ARS scientists online who participated directly in these accomplishments and can answer your questions with more authority. Thank you.